want to know the simple table for the all the conversion of flip-flop? So this is the table, guys. So you guys can remember it, or you guys can easily remember all the shortcuts to find out the conversion from one flip-flop to another flip-flop. So let's get into the. So this one, the SR flip-flop, JK flip-flop, we have already done. So we already find out that S will be equal to JQN bar and R will be equal to KQN. Okay, so this is the thing is that, so here it is the available flip-flop, so here is the decide flip-flop. Okay, so that is what the thing. So here the things are, here is the available flip-flop. So this flip-flops you will be having. So from the flip-flops, so we will be getting the decide flip-flop. So this is the decide flip-flop. So here we already have SR flip-flop. So based upon this connection, we can able to make the SR flip-flop working as a JK flip-flop. So SR to SR flip-flop is not needed. So when we are converting the SR flip-flop to T flip-flop, the S input need to be TQN bar. R input need to be TQN. Okay. So these two resembles, right? So you can remember it. So whenever we are converting the D flip-flop, if it is command, so this is a direct joining of S, and R will be equal to D bar. Okay. So D flip-flop can be converted to J flip-flop. So we already discussed, whenever we have a D flip-flop, the respective characteristic equation of the decide flip-flop is the equation that we have to take in. The characteristic equation for the JK flip-flop is Qn bar plus K bar Qn. So that is what the thing. So SR flip-flop means the characteristic equation of S is S plus R bar Qn. So D to T. So T flip-flop's equation is T XR Qn. So D to T is not needed. So when we want to convert T flip-flop to JK flip-flop, then the T input need to be JQN bar plus KQN. Okay, so simple changes. So here the T input need to be equal to SQN bar plus RQN. Okay, so these two resemble same. So T to T is not needed. So here T will be equal to the D XR of QN. Okay, so JK to JK, which is not needed. JK to S. So J input need to be S and K input need to be R. So here J is equal to T, which is equal to K. Okay, so here J which is equal to D and K which is equal to D bar. Okay, so this is the simple table, guys. So you guys can remember it, or you guys can have any kind of shortcuts, so that, so simply you guys can answer 1 mark or 2 mark if they have asked any kind of things. So here if you guys know and you guys can able to proceed there, or if any new things is added, then we can't use this table. So if the existing flip-flops only added, existing flip-flop only asked, and you guys have this remembered means, then you can easily go over it. So that is what the thing I have to say here. So if they ask today any other new flip-flops, like the flip-flops you haven't here, like only 4 flip-flops we discussed, right? So if in the question they have given a new flip-flop, like they will be giving characteristic equation, excitation table, anything they give, then you have to go with our previous tries. So previously we have done, right? So this is the available flip-flop, decide flip-flop, like that way we have wrote, right? So similar to that only we have to do. So this is only for the existing one, that with already 4 familiar flip-flops only we can do it. Okay, so from here we are completing all our understanding on the flip-flops. So now let's get into registers. So simply registers is nothing but a group of flip-flops cascaded together to store data. So which is nothing but a group of flip-flops. So which is a group of flip-flops cascaded together to store data. So ultimately we have to store data. So flip-flop will store 1 bit, right? So with the help of register grouping, so we can store some 8-bit or byte of data, like that way we can do it. So an n-bit register can contain n bit of flip-flops which can store n bit of data. So based on the applications, registers are classified into 2 types. So one is the storage registers. So which is nothing but to storage the data for temporary or permanent time. So that is what storage registers. So another one is the shift registers. So this one has another one purpose. So for shifting the data or any kind of mathematical purposes to transfer the data, like, so these are the 2 applications. Okay, I hope you guys getting right. So Based upon the input and output, the registers can be classified into 4 types. So based upon the input and types that we are giving, so we can calculate that is SISO, which is serial input, serial output. Second is the SIPO, serial input, parallel output. Third is the PISO, parallel input, serial output. Fourth input is the PIPO, so parallel input, parallel output. So let me go into all of these applications individually. So each one has its own benefit and application. So let's discuss everything. So serial in, serial out. So which is the first thing that we are going to discuss here. So let me take a small kind of example, like how we can demonstrate this is that. So for an example, if you are having 4 kind of flip-flop, let me draw the diagram. So here you will be having a 4 flip-flops. As we know, registers is nothing but a combination of the flip-flops. So we will be having some serial connection or any kind of things. So let me add few things. So here I have taken 3 flip-flops. So here all the flip-flops will be connected to a single clock. So that is the prerequisite. So everything will be connected to same clock. Okay. So we'll be getting output here, and that will be cascaded over everything, because every register's output need to be turned at the same point of time. So there should not be any delay or there should not be any asynchronous behavior. So everything need to be synchronous with the clock. Okay. So this is what. So synchronous asynchronous difference is, synchronous means everything is in phase. So everything, whenever there is a change that is happening in a clock, so every registers need to change its state synchronously without any anomalous behaviors. So that is what the thing. For simplicity, so let me take a D flip flop. So here D3, here Q3. So here Q3 bar. So here D2, Q1, Q2, Q2 bar. So here D1, Q1, Q1 bar. Okay. So this is the 3 things. So if we, so let me add one more also. Let's make a off bit enable. So I have added another one flip flop. So in order to make some off bit byte of information. Okay. So this is the 4th one. So which is D0, Q0, Q0 bar. Okay. So the input will be connected here. Similarly, so this output will be connected to this one. So everything is, the each one's output is connected to next one's input. So because we are going to shift the data here. So because there is a shifting of things. So input which is coming will be transferred to output. So that is what the application that we are going to discuss here. So here in this case, the input is serial. So serially we are giving input. So that is why serial input is given, and output is also taken serially. So serial output. So that's why we call this topology as a SISO. Okay. So for an example, if you are having a serial output data, that is 1011 need to be sent over it. So during the first clock, what will happen? The D will come here. So everything will be under 0 or initial condition. So after this one, so this one will come here, and this one will come here. After that, next clock, this pulse will go here, and then only it will go here. So like this way, this will be going in a sequential manner. For every clock, the output will be changing. So let me draw a table so that you guys can easily understand this thing. So every behavior is based upon the clock only. So this is clock. So this is serial input. So this is serial output. At clock 0, the serial input that we will be providing will be 1011. So this input we need to provide. So this is the serial input provided. So output will be taken like this: Q3, Q2, Q1, Q0. So initially everything is 0. So let's take initially 0 condition. So then what will happen? During our first clock pulse, this 1 will come into this Q3. So 1, 0, 0, 0. So nothing will be changed. Second one, this one will come into this one, and this one will be shifted to here. 1, 0, 0. So this 0 will come here, this 0 will come here. After the third clock pulse, the 0 will come here. So 0, so this one will come here, so this one will go here, this 0 will come here. So after the fourth clock pulse, what happened? This 1 will come, the 0 will come here, this 1 will come here, this 1 will come here. So the input that we are provided here will come to the output only at the nth clock, means number of bit clock. So how many clock pulses that we need is the, so n t clock pulses which needed to move the serial input to the output. Okay, so this is what the thing. So number of bit that we are, number of bit of flip flops is there, right? So that much number of clock times which is needed for us to get the serial input to the serial output. So in right shift register, so this is right shift, right? So every bit is changed to right side. The data applied to the leftmost flip flop, the last flip flop. So here we have applied, right? So this is the thing. So left shift which is equal to data applied to the rightmost flip flop. So this is another one application is the, this is a right shift register. So if we give the data to the rightmost register, then based upon the clock we have to move this way. So then that will be left shift register. So here we have to see the application of right shift register. So SISO can be used to shift the given data or delay the input sequence. Okay, so that is what. So here the two things that we have to take in account. For the entire input to be fed to the system, we need n clock pulse, n t clock. In order to take the output from the system, we need n minus 1 clock. This is why is that. So when the after the third clock pulse itself, we will be able to get this after the third clock pulse, like 1, 2, 3. So after the third clock pulse itself, we will be able to see the data outside. So this is what. So this thing. So let me redo it again. So thing is that, so here you can see the n clock pulse will be taken for us to get the input. So that is the thing. So if we further extend the thing, so let me draw it here. So fifth clock, sixth clock, seventh clock. Okay, then what will happen? If you again shift it for the next clock pulse, what happen? 0, 1, 0, 1. Okay. So next 0, 0, 1, 0. Next 0, 0, 0, 1. Okay. So up to fourth one, we need this much of clock pulses. That means the 4 clock pulse we need to get the input to that. So here if you see, so here there is only 3 clock pulse, so which is nothing but a n minus 1 clock pulse in order to get the exact output that was initially present. Okay, so that is what the thing that I am trying to say. So 0, 0 was there, right? So here n minus 1 clock pulse again we have to give to get the first initial condition. So that is the thing we have mentioned as the output. So in order to get the first state or the previous state, so all the input clock pulses that need to be removed from here, right? So for that we need to apply n minus 1 clock pulse to the input. Okay, so this is what the thing. So now let's see the next application, that is SIPO. Okay, so similar, the same kind of thing previously we done, right? So similar to that only, but here the one thing is that the outputs will be taken parallelly. So here, so let me duplicate this diagram there for your understanding. Let me take up to this. So if it is happened here, so let's take this is a second one. So SIPO. So here instead of taking output at this level, what we can do is that every level we can take the output. So here we will take the output, here we will be taking the output, and here we will be taking the output. Okay, so this is what the thing, but the input, the serial input only, but output is parallel. Okay, so think what will happen. So how we can get the data here? So how many clock pulse is needed to provide the input? That is same as it is, that is n clock pulse is needed. So because the serial input is fixed, how many clock pulse that will be needed for us to take the output? That is 0 clock pulse. So because once this data is fed here, so like 1, 0, 1, 1 is put at here, then how many clock pulse needed to get the data from here is that? So it is just a simple. So this is the fraction of second. So the data is already available. So this is a wired connection. So already this data will be already available. So no need of any clock pulses to get. So similarly these thing. So here the data we have got. So from here we have to remove all the data from the sequence. For that we need 3 clocks. So this is once after the input is fed to all the flip-flops. So here 1, 0, 1, 1 is fetched. So 4 input is given. After that only 3 clock pulses needed to fetch all the outputs. So that is what we stated. In order to turn that into initial condition, we need this much of clock. So similar to that only, now what is needed is that only the no clock pulse is needed, because already this is a direct wired connection. So from where they can directly take the output. So that is what the thing. So extending this, so let's get into PIPO or PISO. So this one you understand, right? So how we are for fetting all the input, we need n clock pulses for n bit. For taking the output, this is already in wired connection. This data will be already available. So whenever there is a change of things happening, the output will be directly fetched. So that's what we are assembling here. So the third one is that parallel input, serial output. Okay, the same thing like previously we fed the. Let me add over it. So this is parallel input, serial output. So here this input is not provided. So this is not. So serial input is not provided. So here we won't provide. This way we will be providing the input. So this way. So each clock pulse will be providing this way, but output is took serially only. So means what will happen? So in order to provide our input, we need one clock pulse, because the initial condition need to be changed, because previously it may be in a 0 0 0 0 state. Okay. So when we apply this one, so then only here also one output. Okay. So this change need to reflect here. So for that we need one clock pulse to take place. So after one clock pulse, all our data will be available here. Okay. But we are taking the output serially only, not parallel output we are taking. So we are taking output only serial. So parallel output but serial output. Parallel input but serial output. So how much clock pulse will needed to get the output? So we know whenever there is a serial output, we may need 1 minus 1 T clock. Okay. So this is very important. So they may ask for each type of register, how many clock pulses needed to give the input and how many clock pulses needed to take the output. Okay. So please make note of it. So then last one, which is nothing but a parallel input, parallel output. So which is very simple. So from our understanding of all the things, so let me explain that in a shorter way. So everything is parallel output, and every input is parallel and every output is input and output both are parallel. So number of clock pulses which is needed to provide input, that is one clock pulse as discussed, and number of clock pulse needed to get the output is 0 clock pulse, because that is already wired connection. So where we no need to provide any kind of clock to fetch the output. So I hope this is understood for you guys. So this is very simple only. So normal observation, like normal analytical, like how the basic understanding of the things. So I hope the registers will be fine for you guys. So in next class, I will be teaching you the universal register. So how we can do right shift, left shift, everything can be done in one circuit. So next class I will be teaching that. So stay tuned for guys. So I hope you guys able to understand all the things here. So if you have any doubt, please post in the comment section so that I will be there to help you guys. Thank you guys. Stay tuned.